Tonight's broadcast brought to you by Death Wish Coffee, when you need nothing but the best.
All right, I've made it all the way to Glencliff Park. And you know what I love about Glencliff Park? Besides the wonderful boardwalk I just took a stroll on, what I really like about Glencliff Park is that it's one of the few places that still has swings. There was a time when Glencliff Park was different. It had this huge house thing, and it was awesome in the fact that it was old and moldy and broken and splintery. Had some of the worst toys to play on ever, and they replaced it with one of these kind of ropes course parks, which some of you when you were younger might have played on. But I came all the way up here because I know they have swings, and that's what we're looking to do. We're gonna get on a swing, and you can get some video of me on a swing. That's my goal. Got my gimbal thing here. I'm looking. Oh, well, you know what you can't do? You can't look like I look. Come to the park with your camera on your gimbal and walk up to a family where the kids have taken up all the swings and say to them, do you mind if I video your kids on the swing? You can't do that. You can't look like I look and say, can I video your kids swinging on the swings? I mean, you could try, but my recollection is that comes across as what we call creepy. And yeah, in the job that I have, coming across as creepy is a non-starter. So we're not going to get the video of Mr. Shelton on the swings. Nope, it's just not going to happen for two reasons. One, I'm not going to wait. I have dinner things to do when I get home. But the other reason, and this is probably the more important one, and I mean this with all my heart, once the little rugrats do get off those swings and I just jump right on them, those parents are going to give me a look, and it's going to come right back to creepy. So we're going to end our little discussion with me packing up all my camera gear, packing up my gimbal, and heading back to the house. But you got a little tour of the park, very little tour of the park, but there it is. Have a great day. See you soon. And here's the intro.
You know when I come back, you know what it look like. Everything lit, all the girls in free. Everybody inside, sipping on a good time. You ain't got a risk, they can put it on me. When they wanna go, they know all my money show. I don't ever get it one way. Yeah.
So it was asked of me to take a look at this problem from a different standpoint, to check and see if this person, actually a couple people, if their answers were right. So I'm going to do that real quick. They just wanted to do the same problem as yesterday, but they wanted to see it if A, I had the fulcrum at the center, and B, the energy answer. The energy answer is the quickest, so let's take a look at the energy answer first. The object would have gravitational potential here and kinetic here. Now, a reminder that we have several things that we can still rely on from our prior discussion yesterday, that we're going to use t for the time, we're going to use x for the length of the ramp, we're going to use theta for the number of times it rolled on the way down in radians, and we were able to derive then r, the radius of the object, as x over theta, and we were also able to derive the acceleration, but I want to be careful here. The acceleration was something that we would use, sure, but we're not going to use it for this instance. So how about I hold off on that for just a moment and not use the acceleration, but use these variables here. The first thing I want to point out is that, we have mgh for the object when it's at the top, and that's got to equal the two forms of kinetic at the bottom, 1/2 mv squared plus 1/2 I omega squared. Now, this means that we need to solve a different motion equation than we solved before, because we need to solve for the final velocity. So let's just take a quick moment and do that real fast. We have the displacement, we have the time, and we have the initial velocity, and we have the final velocity. So that suggests we're going to use velocity equals 1/2 times the initial velocity plus the final, what am I saying? Can't even talk today. Position equals 1/2 initial velocity times final velocity times t, but we know that this is 0. So that's going to give us x equals, why did I put it back to white? It'll have to be that way. No, it's going to be a contrast. I can't do it this way. There. X equals VT over 2. So V is going to be 2x divided by t. No big. We can also then have an expression for omega, since omega is going to be 2x over RT, but R is x over theta. So this is going to be 2x theta over xt, or 2 theta over t. All right, so let's begin. I'm going to do a little substitution here. And that's really it. I'm going to solve this for I, but that's no big. I think, if you really want to see the rest of it, I'll continue. But we just want to get I collected by itself. So I'm going to get rid of the 1/2 real quick because they're pretty easy to cross out. No, let me be patient. Let's go ahead and expand and get 2x squared m over t squared, one of the 2's cancels, plus 2 theta squared I over t squared. And again, we're solving for I here, so this is still mgh. Now, to get I by itself, so move all that up for a minute. I'm going to get my 2 theta squared t squared I equals mgh minus 2x squared m over t squared. And I mean, the only thing we really can do here is multiply by that inverse, and I'll get I equals, t squared mgh over 2 theta squared minus, and the t squareds cancel on the next term, but I'm still going to get 2x squared m over 2 theta squared. So, we organized this a little different yesterday. I factored out the m over theta squared out of both terms, and that left, this being gh t squared over 2 minus, the 2's cancel here, so it's just x squared. And there we go. Was that one easier? Perhaps. But now, another person wanted me to do one more take of this, and this was doing the problem not with the fulcrum, at the bottom, but with the fulcrum at the center. Now, if we do it this way, which is just fine, we're going to have mg normal and friction, but with the fulcrum at the center, the friction is actually the unbalanced torque. So the net torque on the system is going to be I alpha, and remember that's going to be, the friction is going to be the torque this time. So I'm going to get R times F times the sine of 90 degrees for the friction, because the friction's acting, perpendicular to the radius, and that's going to equal I alpha. Now, I can't solve this for I, and I have friction in there. So when you do it this way, you also have to solve the net force problem, which is going to be, and let's be careful here, mg sine phi minus friction equals ma. So the way to solve this problem, remember, is to eliminate friction. And there's no shortcut here. I'm going to do this problem just a little differently than I was doing the problems before by basically focusing on not plugging anything in until the end. Because, to be honest with you, this has already gone a little longer than I intended. So remember, we're trying to get I by itself. So when I do that, I'm going to get I alpha over R equals mg sine phi minus ma. So now I think we can get closer to our solution here. Okay, so there's all of our substitution parts that we need from yesterday to drop into this. So I'm going to have I times 2 theta over t squared all over r, which is x over theta. That's going to equal mg times h over x minus ma, which is going to be 2x m over t squared. So now I just gotta get I by itself. So I'm going to be multiplying and doing a bunch of stuff here. So let's take this and resolve it. And we're going to get I times 2 theta squared over xt squared. Yeah. And that equals mgh over x minus 2xm over t squared. So I is going to be, I'm going to just multiply by the inverse again, and I'm going to get mght squared over 2 theta squared minus 2mx squared over 2 theta squared. And that's it. Same answer. Well, there you go. Enjoy, kiddies.